Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, we'll get started. I'm honored to introduce Ashish Kapoor to you today. He'll be speaking about learning discriminative models with incomplete data. Ashish is interviewing for a postdoc position in the Adaptive Systems and Interaction Group, a 12-month position. I've been on his PhD committee, and I've enjoyed working with him over the last couple of years. He's addressed several issues with kind of eternal problems in machine learning, which especially in areas, domains that he's focused on, including learning to predict human affect and other fusing biometric data of various kinds with contextual data of other sorts, where we have very noisy data. We don't have a lot of effort or energy available to tag all the data, so we have semi-supervised problems, if not unsupervised problems, and labels can be wrong. Mislabeling is common. And the idea is to develop techniques that actually learn to understand those kinds of things and still do okay, and some theoretical methods that can help. And he's taken a Gaussian process perspective on that, and you'll hear about that today. So hopefully that will be that's a nice discriminative description.
Yeah.
And, here we go, Ashish.
Thank you, Eric. All right. So, as Eric nicely introduced me, I'm going to talk about learning discriminative models and incomplete data. And to motivate this, let me give you one of the example scenarios that I have been involved with a lot. So this is an affective agent that's like a learning companion to some person who's trying to solve a task such as Towers of Hanoi here. And the agent observes the users through a number of different sensors like cameras, mouse, pressure mouse, it has pressure sensitive resistors, or physiology, or a pressure sensing, a posture sensing chair. So you get all these observations, and you try to recognize patterns that might correspond to different affective states, and then you have an agent that takes an action based on these affective states. Today I'm just going to focus on the recognition part, and in this kind of a framework, you might have the problem of detecting behaviors before you try to detect the mental states. So for example, we have a face modality, and we have a camera that recognizes different behaviors, such as the shapes of eyes or eyebrows, whether someone's fidgeting, smiling, if you just nodded, shook, or blinked, etc. A lot of these kinds of parameters. Or you might have an audio microphone, and where you might want to detect different kinds of events, whether someone just laughed, someone just exhaled, like kind of thing. So that's frustration, or someone speaking, different kinds of events. Again, you're looking at audio, trying to recognize different patterns that might correspond to different emotional states. There are other sensors, as I said, like pressure mouse, which has pressure sensitive resistors, or posture sensing, which can measure different kinds of posture you are sitting in. And then you have final problem of fusing all these different channels to detect different mental states, such as frustration or interest, or combining a lot of these different modalities. What binds all of these problems is this relationship between sensors. So here we have observations denoted by X's. So these are different video, audio, posture channels. And then you have final class label that you want to associate with them. And the way a lot of these pattern recognition algorithms work is that you first give training examples. So X's are n training examples, which corresponds to different patterns, and T's are the corresponding labels. So the idea is that you recover this relationship between the observations and X's. And today specifically we're going to talk about in probabilistic terms, where we are interested in posterior distribution of label given the observation. So if you can characterize this thing, what happens is, given any new observation, you compute what is the posterior probability of a label. Thus you can classify it. So that's the basic premises. However, the thing is, it's not very easy to get training data. You might have incompleteness. So consider another scenario. It's a multimodal pattern recognition scenario. I have 3 channels here: face, posture, and some context information. And then you want to do multimodal pattern analysis. However, some of the sensors we are working with here is, for example, a camera or posture sensing chair. There are vision algorithms behind it. The hardware might break, as in case of the sensor chair, or the lighting conditions might change so that your tracker fails, or the user just gets out of the way of the field of view of the camera, so you don't have any observations. Hence, you have incompleteness in features. So you have X's in which few of the dimensions of X's are missing because the channels or sensors are breaking. The second kind of incompleteness we're going to talk about is incompleteness due to partially labeled data. So in these scenarios, you have a lot of data, but you don't have resources or time to label every data point. So consider example here, I have 40 or so data points, but only 4 of the data points have been labeled. So the idea is to extract the information from the unlabeled data to come up with the decision boundary. So that's the second kind of incompleteness we are going to talk about. So this is incompleteness is X, and this is incompleteness in the labels. The third kind of incompleteness arises due to the case of auxiliary labels. So consider an image classification task where the idea is to build these part-based detectors which can detect things like wheels or body of the car or windshield, etc. So for training data, you might want to have these kinds of labels. These are the desired label you might want to have. However, getting this kind of label is very hard because it's very manually tedious. Instead, you might have these coarse label available labels. So these labels just says what is foreground, what is background, but they are highly correlated with your desired labels. Here, the task is to use these labels and then come up with classifiers which can classify different parts. So this is the third kind of incompleteness we'll be talking about. And finally, we are looking at a lot of human-computer interaction scenarios, things like affect recognition. The labels, what a human has provided. So you have human annotators looking at these examples and giving you labels. There is uncertainty because of human perceptions of how things have been conveyed to the different annotators, etc. So that's the fourth kind of incompleteness we'll talk about. As I said, the goal is to characterize this relationship between the observations and the labels. And broadly speaking, you can think of 2 paradigms. So first is the generative paradigm, which is trying to first model the joint distribution of all the observations together with the labels, and then use the Bayes rule to come up with the posterior, the quantity we were interested in. However, and the second kind of are the discriminative models, and there are lots of examples such as logistic regression, for instance, or support vector machine is also a kind of a discriminative model, where the idea is to directly model the conditional relationship of the label given X. Whenever you have uncertainty, these generative models, they can just marginalize over these missing data because you're jointly modeling the observations together with the labels. However, you might run into problems when you have observations which are higher dimensionals. So things like, for example, Paul Viola's face detector, it's a case of discriminative model where you are never modeling the underlying distribution of X's. The problem now is, since you are never modeling this quantity, you might have troubles in trying to handle incomplete data. So our objective is to tackle the 4 cases of incompleteness I talked about. So first, we have noisy labels, and then incompleteness in features together with the semi-supervised learning, and also the case of auxiliary labels. Our framework specifically, we are looking at Gaussian process classification and extending that to handle different kinds of incompleteness. So the talk outline, I'm just going to breeze through quickly with the Gaussian process classification right now, just to give you an overall idea. So the way these Gaussian process classification works is that it's a conditional model of labels given you X's, which are observations, and it's related to kernel machines, and there are lots of literature showing how support vector machines can be interpreted, and in terms of Gaussian process classification as well. So there are 2 components of this model. The first is the smoothness constraint you impose. Those smoothness constraints are imposed through these hidden labels Y's, and the intuition here you are trying to capture is that if 2 points, if they are similar, they should have the same label, and they are nicely encoded using a normal distribution on these soft label labels, where K is a matrix which encodes similarity. So the idea is that whenever two points, x's, x1 and x2, if they are similar, they are highly likely that the y's corresponding to them should have the same label. So that's the smoothness constraint, and it has relationship to reproducing kernel Hilbert spaces, etc. But I mean, the important part is what you want to capture is this intuition that same data points have the same labels. The smoothness constraints will be coming back to over and over again. The second part of these models is the relationship between these y's and t's. So this is the place where you encode the information from the label data. So you have some label data, and this is the link where you would encode how these label data affect your final inferences. And the thing is that this is also the place where you can encode any prior knowledge you might have about the noise process. So for example, you might believe that your noisy labels might only occur near the decision boundary. So you can use slack-based techniques as used in logistic regression or probability regression. However, there are lots of cases in which the noisy errors occur because of the human intervention. So then you have other kinds of noise models. But the idea in the Gaussian process classification is to combine the smoothness constraint with the information from the label. So this smoothness constraint is the Gaussian process prior I talked about. So it encodes the intuition that same data points should have same labels. And then you have information from the labels. And here what I'm trying to capture is that the final solutions should be such that which are both smooth but also consistent with the data. And this is a Gaussian term, which is the smoothness constraint, but these guys are not Gaussians. These are non-Gaussian likelihoods. Yeah?
So y is continuous?
Pardon?
Y is still continuous?
Yeah, y is still continuous right now. So so you can take a sine of y to compute the final decision or use some Bayesian averaging. Computing this quantity might be hard, so we are going to use expectation propagation, a way of approximate inference. And rather than going into the details, the intuition behind it is that you approximate all these non-Gaussian likelihoods using Gaussian approximations, and this is a message passing scheme. Today specifically, there are two byproducts that we are going to exploit from this algorithm. The first byproduct is an evidence. So evidence is nothing but a normalization constant of this posterior. And it is a numerical quantity that signifies how well a model fits the data. So there might be parameters in your model which induce similarity, such as kernel functions. And so there are hyperparameters that you might want to find for that kernel functions. So we are going to use evidence to find those right parameters. And the second the second byproduct are these Gaussian approximations to these likelihoods. So we'll be looking at a case in which we'll be modifying our training and testing data sets. So whenever you modify a training data set by adding a point, all it boils down to multiplying a Gaussian term to compute the posterior, and these are computationally very feasible. I'm going to go into details soon, but these are two of the byproducts we should keep in mind. So this is one simple example where we are trying to detect an affective state depending upon a number of different sensors, and it's an affective state induced by boredom. Imagine you're playing Towers of Hanoi and you cannot really get it done. So you come into this state of frustration, anger, and you say, all right, I just want to quit. I don't want to deal with it. So that's the kind of state we are trying to recognize, and there are a number of different sensors here. So pressure mouse, physiology, posture sensing, face. This is a very small data set we have, 24 subjects, 10 class 1, 14 class 2. There are 14 features we have extracted from all these modalities. The thing is, a priori, you don't know what features are important for this kind of classification. So to induce the measure of similarity, we are going to use a kernel function. So xi's and xj's are 14-dimensional vectors. And what we have done is, this is a measure of similarity, where each kth dimension has been weighted by some hyperparameter sigma here. And our challenge is to find the right features so that we can classify this task well. What we are going to do is, we are going to exploit the evidence I talked about. Evidence is, again, as I said, is a measure of how well a model fits the data. So use evidence maximization, try to find those sigmas using any nonlinear optimization techniques which maximizes your evidence, and apply in the Gaussian process classification framework. So you can get, on this task, you can classify like 80% accuracy. However, this is just an example. we are going to get into more interesting stuff after this. The first thing I'm going to talk about. Yeah, sure.
So how, when you did the classification accuracy there, did you do a cross-fold analysis? Did you do a whole outset?
Oh, so basically, the results I'm showing is leave one subject out, train on 23 subjects, and test on the 24th subject, and repeat for all the subjects. No? So that's the strategy.
Okay.
Yeah. Sure.
On that equation you had before, is it as simple to say that once you determine the sequence, that
Yeah.
it tells you which?
Yeah. So in this task, the most important feature that came out to be was the postures. So if you are slumped back, it's kind of you give it away. So let's talk about the incompleteness in features right now.
Can I ask a question?
Yeah,
While
sure.
we're in that
Sure,
mode?
sure.
When are you making the classification? Because presumably they're not bored from the beginning. and
Yeah,
they
yeah.
become bored at some
Mhm.
point.
Yeah. So the thing is, we are looking at a time window after 225 seconds. So that's the time window when most of our subjects did quit. So empirically, I mean, we thought, all right, this is a time frame when either people get really bored. So again, but ideally you want to have a continuous thing that goes on. But the thing is, this interaction is very dynamic, and the agent first comes in, and so the context is also changing. So you can imagine building these classifiers, which also are dynamic over time. So, but that's work for future.
But in this, so you're just taking one snapshot of the features at 225.
Yeah. It's a very simplistic scenario. All right, so let's talk about the incompleteness in features right now. Again, this is
I only see one person slumping right now, I think.
It's-
It's
yeah. So there are multiple modalities, as I said, that they are missing features because of sensor failures, etc. As I said, we have vision sensing, which breaks down due to change in lighting. So this is a graphical model just describing the Gaussian process classification. We have x's, so here ith example, and we might have some unobserved features because of these sensor failures. And this is the final label. This is the label that has been given to us for the training. The thing is, we are never modeling the underlying distribution of x. We don't really want to do that. So how do we tackle this kind of incompleteness? There have been some work on trying to solve this problem. So most popular way is imputation. What you do is you use some ad hoc rules to fill in your unobserved features. So for example, fill zeros wherever everything is unobserved, or -1, or maybe the mean, or the previous value. So there are a lot of rule-based systems that use imputation. There have been some recent work on kernel completion using semi-definite program. So whenever you have unobserved features, you can't really compute those similarity measures. So if you think the kernel matrix, that's incomplete, so you want to complete that. The problem with some of these approaches is that if your kernel matrix is very sparse, they might have trouble. And the third thing is, a lot of people do that, is just, why not just model the underlying distribution of observations and we'll marginalize out the unobserved features. The problem is that one of the advantages we had in higher dimensional data with discriminative models is that we never model this thing. So going back to it is kind of, and sometimes might be harmful. So there are approaches, a very recent approach using mixture of Gaussians for logistic regression. And in statistics, there is a book just talking about these models. So basically, it's in surveys, you might have non-response. So they have models that can handle these problems. But the problem is they're trying to model this distribution, which we don't want to. So, yeah?
Sorry.
Yeah, sure.
So first, a simple way of doing this that comes to mind is to just sample the complete data. And
Yeah.
just say,
Yeah.
I didn't observe this.
Right, so that's what these techniques are doing. So what they do is just sample from the complete data and try to, but the problem is that you're modeling this distribution then. And if you have not enough data and you have very high dimensional observations, this can run into problems. We're trying to propose a problem in which we don't have to go through this route.
So they're still modeling the joint.
Yeah.
You could train the discriminative classifier like this, right?
Pardon?
You could train a discriminative classifier where you just say, this feature is an asterisk.
Mhm.
I don't know it, but
Yeah.
I just train with that information.
Yeah. The thing is, once you're sampling from a distribution, so you're saying that,
No, for my training data, I just go and replace features
Yeah, so it becomes a special case of imputation, where you are using some rule-based technique to fill in your missing features.
No, quite the opposite. I actually believe features that I've seen in the training.
You seem that you train a new classifier where you just ignore that particular feature if you have
Yeah,
cases.
well, you actually gave away my talk. That's what you're going to do. So basically, that's what we're doing. We have a mixture of Gaussian process classifiers here, where we are training individual classifiers on individual subsets of features and then combining the decisions. So that's the basic idea. Here we have Gaussian process, one Gaussian process. Now you can have multiple classifiers trained on a subsets of features, and then you're going to combine them, right? And there are multiple ways of combining. You can use fixed rule-based methods, such as multiplying the product, or like taking the product of the probabilities, or voting them, or taking a sum, etc. Or you can use things like mixture of experts, and there are lots of work recently in Eric's group as well, where the idea is to use a mixture of expert formulation. So here we have, we can have Gaussian process smoothness constraints on each of these, links, which are induced by subsets of features, and then use a combination rule. So this is lambda is a selector, sort of random variable, which selects what subsets of features I should use to classify this data point specifically. Just to give you a brief intuition how these mixture of experts work is that in the feature space, so these are points in the feature space, so you partition the feature space into different regions, and you would train different classifiers on different regions of the space. So whenever you have a new data point, first you figure out what region it belongs to. So for example, I might have this is a test point, and it belongs to a region where we know that the posture sensing classifies the best. So we're going to use the posture sensing to classify that point. So you can think of an expert critique kind of a framework, in which first you have a critique which takes a look at an input data point and decides what is the classifier is going to work, what's the classifier which is going to work best on this data point. And then you have experts trained on individual regions. The problem with this kind of formulation is that there's a chicken and egg problem. If you've been just given a training data and you don't know any kind of partitions, there is no way to train these experts because you don't know the partitions. And if you don't know the experts, you cannot find the partitions. There's a chicken and egg problem. Yeah? Okay.
Can you have regions where you look at more than one feature?
Yeah, you can. Ideally, these should be all possible subsets. That will be the ideal case. But for a practical problem, you might have impose some heuristics. You might know that some features don't correlate well at all. So you can impose your prior knowledge in the problem on these things. So as I said, we have a chicken and egg problem. So a very simple way to tackle these things is, like, for example, an EM algorithm, where what you do is you take all the data set without considering any partitions, and you train all the experts using all the data. And once you have these experts, you first find out what are the relevant partitions, and then you refine your experts again, and then you iterate, right? So this is an instance of EM algorithm. However, the problem is this step of training and retraining might be very expensive. If you're using support vector machines as your base level classifiers, and you're using million data points, this can be really expensive. However, here we are going to use the trick of those Gaussian approximations of those likelihoods. We are using Gaussian process classification. So whenever you are partitioning the space, it all boils down to removing or including some points from your training data of your experts. And since we had those Gaussian approximations to those likelihoods, you can multiply or divide those things very quickly. And this is a very quick, so basically it's a very quick operation. So again, to formalize it, for each expert, we use all the data to first come up with with these Gaussian approximations using expectation propagation. And whenever you have to update our experts based on regions, all it boils down to just removing and adding these points, which is nothing but multiplying and dividing your likelihoods. So it's a very efficient way of training. The database, so let me show you some of the experimental results we have. So this is an affect recognition scenario. We have multiple channels, some of the channels are missing. And there are 4 channels. So upper phase, lower phase, posture, and the state of the game. it's a two-class problem trying to detect interest, and we have lots of missing channels, a lot of missing data. And what we are going to do is we are going to compare these strategies with first a rule-based classifier combination methods. So these rule-based methods just use sum rule, product rule, vote rule, etc. And then the other thing is what you can do is you can also do feature level fusion. So we have all these different dimensions with some of the dimensions missing. You can use imputation-based strategies. For example, fill -1, which corresponds to error, and then train a classifier on the joint features altogether. And of course, we have the mixture of Gaussian process framework. So if you look at the results, so for the test, what we did was we did 50% training, 50% test split, and we repeated this 50 times. And here I'm plotting the means as the dots. So this is the recognition accuracy. The error bars corresponds to standard error scaled by 1.64. So whenever the error bars are not overlapped, they mean 95% significance. So the mixture of Gaussian process obtains around 87% accuracy, beating both the feature level fusions, most of the fixed base classifier combination methods, and a method based on a hidden Markov model, basically. So the thing is, since this method is sensitive to where the errors are, it performs better. But the bigger question is, does using data with incomplete features buy you anything? Should we just discard all the data that was bad, just train a classifier on data that was good, and see how well that performs? And so for that, what we did was we compared against a feature level fusion in which we are discarding all the data with all the partial observations. So this is all clean data, no missing channels at all. So if that's the case, and if you compute and if you compare feature level fusion with the mixture of Gaussian processes, so these are again 50 runs, and each point in the scatter plot corresponds to recognition accuracy obtained by feature level fusion versus the mixture of Gaussian processes. So whenever a point lies above the diagonal, it means that for that test and train split, mixture of GP beat the feature level fusion. Otherwise, it's the vice versa. So looking at the scatter plot, you can see that there is no performance reason to prefer one classifier over another. However, mixture of GP is slightly expensive. So in these cases, for computational reason, you might want to prefer those. But when you introduce all the data with missing channels in dwell, you see that this cluster has been bumped up on the diagonal. That means that what's happening is both of these methods are getting benefit. However, mixture of GP should be preferred now, because it is slightly sensitive to where the errors are, and it can choose channels wisely. So to summarize this, what we have is we have proposed extension for Gaussian process classification using this mixture of experts scheme, and the key feature is this fast inference by exploiting the EP approximation. So you don't have to retrain your classifiers over and over again, and we get a good recognition accuracy on this affect classification task. With this, I'd like to move on to the second kind of incompleteness. I already talked about this incompleteness when I visited here last time, so I'm going to just breeze through this very quickly, but feel free to interrupt me if you want more details on this. As I said, we are looking at a semi-supervised case where we have a lot of data but very few labeled data points. Supervised classification techniques, if you ignore all these labeled data, might come up with a decision boundary like this. But the thing is, in semi-supervised learning techniques, you want to exploit information from the unlabeled data as well. And Gaussian process classification, traditionally as they're defined, as I said, there are two components. First is the smoothness constraint, which does not depend upon the input data distribution, and there is only information from the labeled data point that gets fed into the model. So there is no way they can actually exploit the information from the underlying data density. So one of the things a lot of people have been doing in a number of different optimization frameworks is use a smoothness constraint that depends upon the underlying data density, and it's called input dependent regularization. We are going to call it data dependent priors, and these have connections to a lot of these new graph based semi-supervised learning methods that have come up, and where the idea is that given a data set, you induce a similarity graph. So here all these vertices corresponds to the data points, and we have induced edges which which represents similarity between two data points. So basically the thing is, once you induce this graph, you can use a lot of different optimization based strategies, things like graph cuts or diffusion processes or random walks. Starting from these label data points, you can take random walks, thus diffuse information throughout the graph and come up with appropriate labelings of different data points here. As you might suspect, the key thing in many of these approaches is this measure of similarity. And the way a lot of these algorithms work is by using the concept of kernel to induce similarity on two data points. So for example, it's like RBF kernel. We have xith and ith and jth data points, and similarity between those 2 points might be captured using a kernel matrix. It might have parameters such as sigmas, which determine how similar 2 points are. And to just give you an example how critical the similarity might be, this is a toy data set. I have one class which is a semicircle, and I have other class which are 2 clusters. We have 3 label points for this data, this cross, and this blue label. If you use the right value of your kernel, you get perfect classification here, 100% classification just using the 3 data points. And this is, LLGC is one of the recent algorithms that was introduced. Very simple, very powerful graph-based technique based on random walks. And if you just slightly change the kernel parameter, you get drastically different results. The thing is how to compute this measure of similarity. In SVMs or other classification techniques, you might have cross validations, but you have only 3 labeled examples here. There is nothing to leave out. So what do you do? Other problem might be the noise. So again we have 2 classes here, class 1, class 2, and they are noisy labels. So these are all blue, these are all red. This should have been red, but is blue. This should have been blue, but this is red. So you have noisy labels here. Imagine if you're just using the random walk analogy or diffusion process, these noisy labels would break those processes. So you need appropriate noise model to handle these kinds of things. So again, if you use LLGC, which doesn't have a very good noise model, the random walk breaks, and you don't get a good classification. So there are 2 problems with some of these techniques. One is if you're violating the cluster assumption, if you have noisy labels, you can break the random walks. And again, as I said, the hyperparameter estimation, which is hard because you don't have much data in semi-supervised cases. So what we are going to do is we are going to look at this problem in a Gaussian process framework. So we'll have this tool of evidence, and we can exploit evidence maximization to learn these hyperparameters then. So the idea is very simple. We are going to modify the smoothness constraint. The first smoothness constraint said that if 2 points are similar, they should have the same labels. We are going to change the measure of smoothness by introducing this quantity. So we are going to say is prefer solution which has the small value of this quantity. So here all you are saying is that 2 points are similar. If 2 points are similar, they can't drastically have different values of y's, but you are also summing them from all possible pairs of unlabeled and labeled data points. So the thing is, you can write this quantity nicely in terms of a Gaussian distribution. But however, the key intuition behind is that the measure of similarity has now incorporated the manifold. So now you are looking actually the similarity over a manifold rather than similarity just over a feature space. So that's the key difference. Again, I'm rushing through this because I presented it here before, but if you have any questions, just please feel free to interrupt. And again, you have all these noise model where you can handle different kinds of noises now. So basically the thing is, we'll be looking at the flipping noise model, and it's just for convenience rather than anything. You can use any of these different noise models. One of the good things about this method is that there are a number of different approaches that does semi-supervised learning. These are all graph-based approaches. We can interpret all these approaches in a Gaussian process framework for a different choice of regularizer, different choice of noise model, and different choice of other transformation parameter that modifies the graph Laplacian, which is, this is a little bit secondary. But the key point is that all of these methods can be interpreted in this Gaussian process classification framework. Thus, all the parameters in these methods, you can use the same framework to actually find the right parameters and come up with a good classification. As I said, we are going to explore evidence maximization, where the idea is to maximize an evidence. Here, thetas are different kernel hyperparameters, the measure of similarities. There might be parameters in your noise model. There might be other parameters, and finding the right set of parameters which maximize this quantity. So we are going to use an EM expectation maximization based algorithm rather than going into the details. I mean, it's you can use any gradient based descent or any nonlinear optimization as long as you can compute gradients, Hessians, etc. of this quantity. All right, so first let me show you if evidence makes sense to actually choose all these hyperparameters. So on the x-axis, what I'm doing is I'm varying the hyperparameter sigma of my kernel, and these different plots corresponds to different number of data sets I might have in my label data, and this is the log evidence. So as I vary the kernel width, you see these, there is a maximum that is reached, which is the most likely, this is the place where the model fits the data the best. As you increase the number of label data points, the curve becomes peakier and peakier, so showing that there is much and much, it becomes more and more confident as you see more and more data. Even with very few label data points, like 6 label data points, you have this kind of bump, which tells you that you can actually use nonlinear optimization techniques to maximize this quantity. But more interesting thing is that this evidence curve correlates highly with the recognition accuracy on the unlabeled data. So here, the blue is an evidence curve, and this the purple curve is the recognition accuracy. So showing that you can actually exploit evidence maximization to learn the hyperparameters, and you can see this across number of different data sets. So this is handwritten digit data set as well as news group data set. Again, this is not perfect. We might have maximums which are a little bit off, but it gives you a nice framework to deal with hyperparameter learning. And you can actually compare evidence maximization versus leave one out cross validation, specifically when you have low number of available labels. So here I am plotting the error on the unlabeled data as you vary the number of available labels. When you have very few labels, the error obtained by evidence maximization is significantly better than if you use leave one out. The reason is you don't have much to leave out, so these are, it's not going to work well. That's the intuitive explanation. However, as you have number of labels that are increasing, those both curves converge. I mean, leave one out is perhaps a better measure, and evidence have been shown to be prone to overfitting, etc. But again, if you have very few number of labels, evidence might give you a better, basically a better measure. And then you have the case of handling the noisy labels. In this example, you can again use evidence maximization to tune hyperparameters, and you can actually figure out that they are noisy labels and come up with a good decision boundary using the Gaussian process classification. So why I'm really caring about noise? Because I have affect data, and the labels can be noisy because data was annotated by humans, and there's a lot of manual intervention going on. So to actually confirm that this is the case, you can plot the evidence of the model as you vary a parameter that indicates how much noise was there in the data. So this is a parameter that encodes there is some noise, the amount of noise in the data. It actually maximizes at 0.05, indicating that there might be 5% labels which are noisy. But again, this is just this is what the model says. The model might not be correct, but it sort of tells you that there might be some noisy labels in the data. What you can do is you can try to use different algorithms on this data set. So as you vary the number of labeled data points, I'm plotting the error on the unlabeled data. The first method is the Gaussian process classification using expectation propagation and a noise model, which is a flipping noise model. The second algorithm I'm comparing against is LLGC, which is a random walk based method. These two algorithms have the same smoothness constraint. The only thing they vary is how they handle the noisy labels. And then we have SVM, normalized Laplacian. So basically the smoothness constraint, you can make a kernel out of it and put it in a support vector machine based algorithms. So again, this also has the same smoothness constraint. The only difference is the noise model. And for baseline purposes, we also have SVM, which is just a regular RBF kernel. The parameters for all these, for EPNL as well, was computed using evidence maximization. For rest of the methods, it's using leave and out cross validation. So as you see that as you increase, so EPNL is working one of the best, but as you increase the number of labeled data points, it sees markedly significant improvement. The reason is that now your training data set starts seeing more and more noisy labels. So if you don't handle the noise properly, you might suffer in performance. So by handling the noise properly, you can actually get a significant advantage. So to summarize, basically, we are using semi-supervised Gaussian process classification using input-dependent regularization and connecting a lot of different graph-based methods. The key advantage is that you have evidence maximization now, which you can use for hyperparameter tuning as well as to handle noisy labels. So things like an affect classification and a lot of HCI tasks, you might have significant advantage. With that, let me talk about the case of auxiliary labels, where we are trying to learn the parts discriminatively. As I said, we have consider the task of classifying each individual pixel in this image in terms of parts. So the first is just the detection, and then once you detect it, you also want to classify what different parts there are. The thing is, there is a lot of structure in this data. So for example, these cars, they have parts, right? So they have wheels, they have bodies, they have windscreens, etc. And also there is spatial structure. The spatial structure is that if, for example, consider pixels here. If a pixel is a background pixel, all its neighboring pixels should be background pixels unless there is a strong edge. So basically there's a lot of spatial structure in it as well. If you can take into account the structure, either the part-based or the spatial structure, you can actually gain a significant advantage, as we'll see. However, the problem is, where do you get the data annotated for parts if you want to encode the parts-based structure? The thing is, you have to come up with a training set where each and every part has been annotated, and which can be really hard. And again, in this case, it's clear that what are the different parts of the car, but there might be other cases where it's not so clear. So for this, what we're going to do is we are going to introduce a model. So the very naive thing, if I'm just using a Gaussian process classifier, what I can do is I can take an image X and classify each individual pixels depending upon these Gaussian process classifiers. So these Gaussian process classifiers, given some annotated training data for parts, they just learn these classifiers. However, the thing is, there is no spatial structure, and if you don't have the parts annotations, they cannot really handle these things well. So to actually encode the spatial structure, you can go to conditioned random fields like formulations, where you are inducing constraints between adjacent pixels. So here you have a case where you can handle the local spatial structure well. However, if you don't have data annotated for parts, these models are not going to take care of those situations. And then you have the case of hidden random fields, where you introduce these hidden nodes, which corresponds to different parts you might have in your data sets. So at the training time, you observe as X, the observation, and these auxiliary or course level labels. And our goal is to infer these parts as well, the classifiers that can classify these parts. And so this is one of the recent advancements. So this is the model that Martin Zoomer has used, and also I know some of the people at MSRS have also used. The problem is that this can take into account the parts, the local spatial structure, but you might also have some structure which imposes long-range dependencies. For example, in our object segmentation task, knowing a wheel greatly constrains where the rest of the car can be, because the wheel is always at the bottom of the car, provided that you have straight photographs of cars. So we want to impose those long-range dependencies as well, and the way to do it is through the model we are proposing using located hidden random fields. So here what we have done is, besides our X's, the labels, the part label and the auxiliary label, we have introduced these nodes which actually encode the compatibility between parts and the locations. So for example, if a part occurs in an image, there is a certain location it can occur in. So those are the kinds of things they encode, and they are connected through a supernode which actually encodes the position of an object. So to clarify these things clearly, let me go through this model. So first you have x's, and you're encoding the compatibilities between each individual pixel and what part they can be. So these are, think of the unary classifiers. However, as I said, there might be spatial constraints. So that's what encoded by these edges, where you're encoding how two parts are compatible. So for example, wheel only can lie near a car body. It cannot lie near a windshield. So those are the kinds of relationships you're encoding here. Then you have relationship between parts and the auxiliary labels. So if I'm observing just background versus foreground, there is a certain kind of constraint I'm imposing on the parts. So this is, and here this can be a deterministic relationship, or it can depend upon your end application. And then there are these compatibilities between parts and locations. So if I'm a wheel, where can I lie in the car? It can only be the bottom. So those are the kinds of relationships. So again, to show you exactly, we have images x's. These are the auxiliary labels which are getting. So these are not part based. So this is just background versus foreground. If you would like to think a coarse label labeling. And we have a location map. So here each different color corresponds to different location in a reference frame. So for example, this red might correspond to some position here. So what you want to do is you want to encode compatibilities between wheels, and so parts such as wheels and the location. So for example, if we learn this model properly, our model would learn that if a part is a wheel, the location map it can take is somewhere around here only, not the blue ones. So these are the kinds of compatibilities you want to impose. Again, there are a lot of parameters which describe these relationships between adjacent pixels, between parts, between compatibilities represented by theta. And again, what we're going to do is we have a smoothness constraint, which is similar to the smoothness constraint in the Gaussian process prior. The smoothness constraint together with how well your parameters are consistent with the observed data. So this is again the objective function. So here, rather than looking for a Bayesian solution, we'll just for simplicity go for a map solution where we're trying to find the most likely solution. And you can use a gradient descent algorithm to do that. Computing this function can be tricky because you have an image and you have high tree width here. So you can use techniques such as loopy belief propagation, and that's what we are going to use here, some product version of loopy belief propagation together with some variational message passing. We can evaluate, using those techniques you can evaluate the function together with the partition functions as well as the gradients of this very effectively. And in an optimizer, we can learn all the parameters in 2 hours for like 35 images. Still a hard problem, but I guess it's fairly doable. Okay, so let's look at the parts. Let's look at some of the results we've got. So we have data sets like these, so only looking at the side view of the cars, just for simplicity, all scaled, cropped images, and we have auxiliary labels for these. So what in the model you can specify the number of parts you want to learn. So if we just learn 2-part model, you can see that our parts recognizer comes up with 2 kinds of classifiers. So the first classifier recognizes that there is a top of the car and there is a bottom of the car. Whereas a 3-part model says there are 3 parts. There's a top of the car, there are wheels, and there's the middle of the car. Whereas the 4-part model, it actually splits the top of the car into 2 parts, like forward and the bottom, forward and the backward, basically. So again, just by using the auxiliary labels which are coarse, we've been able to learn parts which corresponds to different appearances as well as are informative about the locations. And then you can actually compare it with the different number of models I showed you. If you just use Gaussian process classifiers without taking into account any kind of structure, and if you're just trying to classify foreground versus background, you don't do well because you're not exploiting any of the structure in your data. You can use CRFs to do it, and then you might have shrinkage or you might have bleeding because it's only imposing short-range dependencies, not the long-range dependencies. You might have hidden random fields, which kind of learns the parts, but it's not imposing any long-range dependencies. So you might have again bleeding and these kinds of things. However, if you're using long-range dependencies, you can actually segment out things very well. And in fact, on a benchmark data set, you can actually obtain recognition results, segmentation results using discriminative model, very comparable to some of the generative counterparts, which are the state of the art. And then you can also use this model for detection in cars, for detection cars in the image or other objects. And so if you plot ROC curves on a benchmark data set, you can see that as you increase the number of parts, your performance increases. So the thing is that you have a lot of structure in the data, and you're exploiting that structure. We kind of saturated at the 4-part model, and so here we just plot the 4 parts here. And you can also compare it with existing techniques, and so these are some of the existing techniques. Our method is in the black. There's only one method that beats this method. The reason is this database has multiple objects in the car, and our model as such cannot handle multiple objects. But we have used some heuristics. But the key thing is that with the very few training data set, we can actually get very good recognition, very good EER rates. And the reason is because we are now learning parts rather than trying to build classifiers that detect the whole object. Building parts-based classifiers is easier because there is less of visual variability. So for example, the wheels. You might imagine that you can make a wheel detector very quickly by only using 20 samples, but making a car detector with 20 samples might be really hard because it's so complex. So you're trying to find these simple classifiers, hence you can get away by using very small training data set. Yeah?
So for the cross-communication experiments, we could also just use some standard EV segmentation, like graph cuts.
Yeah.
Just to throw in the graph cut and the images, you get some patches.
Yeah.
And you can force them to combine the patches.
Yeah. There are techniques. So for example, CRF is a case of that. So your graph cuts, right? The CRF is actually imposing same kind of constraints on it, and here the thing is, CRF is the method you just described. It's taking into account the local spatial structure, but first you also want to learn the parts. That's one of the advantages, right? And the second thing is the long-range dependencies. If you don't have those long-range dependencies, you might end up with these kinds of things. So the biggest advantage, the biggest win we are getting out is by imposing long-range dependencies together with the parts. As I said, if you know that the wheel is here, there is no reason for me to think that the rest of the car can be here. For example, the CRF or HRF, they can identify that this is the bottom of the car. But since they don't have long-range dependencies, they basically, you have these kinds of regions. However, if you have long-range dependencies, you can exclude these invalid hypotheses altogether. Okay, so these are some of the examples from very low, this data sets where you have multiple cars, you can segment and detect cars very, nicely. So to summarize, is the last part of the talk basically is that we have, extended discriminative models to handle these structure in the data. These are spatial structure as well as the part-space structure, and we've shown applications to computer vision basically. The key thing is modeling these part-based structure together the short-range and long-range dependencies. And to summarize, you can think the whole the scheme I just talked about in terms of this graphical model, where we have different subsets of features, we have some smoothness constraints, we have some model of noises, and we have T's, which are the labels we're interested in, and Z's are the auxiliary labels that we might have available. And the 4 cases of incompleteness I have talked about arises by choosing different subsets of features. So for example, in regular Gaussian process classification, I say there is only one subset which have all the features. We are going to use a regular GP prior as a smoothness constraint. You can use any noise model, and then you observe T's So this column doesn't matter. Similarly, for incomplete features, you might have multiple subsets, again a regular GP prior, and you can use any noise model. For partially labeled data, the only difference is the difference in the smoothness constraint. So now you can imagine you can combine incomplete features together with the partially labeled data. So you have these mixture of semi-supervised Gaussian processes. So you can actually do classify combination in semi-supervised setting seamlessly without really changing any of the problems in the framework. And then you can also extend it to the case of auxiliary labels by assuming that you're observing some z's and you have a relationship between z's and t's. Well, to end the talk, we talked about the 4 different kinds of incompleteness. First, we're just going to use Gaussian process to encode the noisy label cases, and you can extend those Gaussian process classification using incompleteness in features by a mixture of Gaussian processes. And then we use input dependent regularizations. And finally, I showed the located hidden random field that tackles the case of auxiliary labels. So there are a lot of future work, both in applied sense. There are a lot of application in sensor networks, for instance. You have a lot of cases where you might have incomplete data because it might be, because of the power issues or because of the environmental issues, you might not have access to the complete data. So you have a lot of applications there. Application activity recognition scenarios, HCA applications where you have human intervention, where you might have noisy labels, or you might want to reduce the amount of labeling effort by a human. You can use these techniques. Some theoretical issues using approximate inferences, etc., some hybrid models. And one of the things I've been thinking of is this decision theoretic perspective for cost and benefit trade-offs. There are some labels which are easier to get and some labels which are extremely expensive. Can you actually incorporate those costs in your problem formulation? Well, with that, I'll just conclude and take any questions you have. Thank you. Yeah.
In working on the missing labels problem,
Yeah.
that kind of suggests to me that it would be cool to have an interactive program where the process runs along and says, well, here's one label that is especially puzzling. And,
yeah.
Could you label this one for me? And
yeah.
if you did, that would really help a lot.
Yeah. So that's a classic case in active learning, and people have been looking into that. So the good thing is we have this Gaussian process classification framework. So with every classification, you also get a variance. So it's you can think in terms of a confidence, how confident an algorithm is. So you can take into account some of these measures, and this is one of the things I want to do specifically consider a computer vision case. You have for example, I have a video, and as we know that a lot of videos make a manifold over the space. So you can have semi-supervision. However, if you want to do a tracking on the video, rather than trying to label all the video frames, you might decide to annotate like couple or 4. Now, if you incorporate the scenario you suggested, the active learning case, the algorithm can tell you that if you label these 3 or 4 frames, I'll get a very good performance. So there are lots of applications like these, and yeah, that's one of the future directions I'm looking at. Yeah.
In the case where there are voice labels,
Yeah.
so basically some labels are wrong. So I wonder if you could test a case where there's maybe 20% of the labels are wrong.
Mm-hmm.
In that case, the distributed model may not work.
May not. Well, I should actually show you one of the examples. I have handled cases till 20-25% noisy labels, and one of the things, for example, consider this image classification task. So, for example, this grab cut, right? The grab cut. This is a program that you say this is the foreground part of the image, and you can pose it as a pixel classification task, whether each pixel is a foreground or background, right? So you can have the same problem framed in terms of a discriminative framework, and you say, all right, this is roughly what my foreground object is, and you give it noisy labels. So, for example, in cars, you get, all right, you cover windows, or you just draw a box around it, and there are a lot of noisy labels now, and these are the cases. I have some simulations. I can show you the results. Yeah, yeah. I mean, well, I can show it to.
Yeah,
Well,
sure,
yeah,
I
yeah.
got
But
it.
basically, what you can do is you can use these techniques to find out where the mistakes in these pixels, and it actually gives you the complete segmented out object directly. So, but the problem is, as you with 30-40% labels, it might get harder, and then you might want to combine generator models together with the discriminative models. And that's a valid point, actually.
So
Yeah.
if I got you right, so basically, in order to deal with these noisy labels, you use like this manifold kernel.
Yeah.
You have like.
Yeah.
So how do you decide the size of the kernel? Because if you have it too big, then you want to start to mix labels from two different clusters.
Mm-hmm.
So do you learn the size, or how do you?
You mean the kernel parameters?
Yeah, I mean, because basically
the,
you
the,
take
li-
a
the rise
whole
of the
system.
kernel, right?
Exactly. I mean,
Yeah.
the
The kernel width, right?
Yeah.
Yeah.
How
So
do you decide that?
so that's the evidence maximization we did. So when I was describing the semi-supervised learning, so the similarity that's captured by the kernel width, right?
Yeah.
And there are parameters like kernel width to that measure of similarity. So we look at evidence to do that essentially.
I mean, but what I'm saying is that basically you have two different parameters. One is like the measure of similarity between 2 points.
Yeah.
And then how big is your manifold? I mean, how many like?
How many data points you have in the manifold?
Yeah, exactly.
Yeah, I mean that's
How
currently
do you learn that? How do you decide that number of points?
that number of points. So I mean, in classic semi-supervised case, you've been given a lot of data, and we use all the data points.
So I mean,
Yeah.
you all the data.
Yeah, we're using all the data points. But I mean, I can see why you might want to select only few data points rather than use all.
Yeah.
And yeah,
you
yeah.
can start to have problems there. Right?
Yeah, you can have, for example, in Gaussian process classification, you might have problems in inference because your matrix becomes, with expectation propagation, if you have a lot of repetitive points, it runs into problems. So there are scenarios in which it's desirable to use only a fixed number of data points. But that's the problem, we haven't looked into it yet. So.
Great. Thanks again.
Thank you.